on. Yeah, so those are slides from meetup in Los Angeles, where we were like explaining basics of technology to complete novices. Plus, also we were talking to some students who want to train themselves to pass job interviews. Because I interview like many students, and what I found, like even when students go through regular introductory classes in digital designs, when they come to electronic company, they struggle in certain areas, and they know those areas. So we created examples which help them to pass interview. Specifically, those areas include like pipeline designs, which are common in industry, but they're not taught to a good degree in universities. And plus also students even in top schools like Stanford are not properly taught to do verification, so they cannot check their results. And I was talking about this in meetings with students. So this is a little bit about my background. So I'm a chip designer. I work at Samsung, and I was the founder of EDA startup. And so here is the levels of understanding. So here are different FPGA boards. Huh? Yeah, but basically the setup we are using on like introductory classes. Yeah, so the setup we are using on introductory classes looks like this. So basically we give everybody in the audience a little FPGA board, which is a 10 nano 9K FPGA board, and a little graphical screen, LCD screen, and like interface module which has like buttons, keys, and seven segment display. And like I have the whole bunch of such FPGA boards. And the good thing about this setup that it is very inexpensive. So those parts together cost like $25 or something. And like usually introductory FPGA boards for students in many schools, they use like Nexus A7, which costs $350, or something else. And so with these boards you can teach this thing even for like school children, because you can just spread them a lot. Now we also in order to like avoid too much struggling with the setup, in a class we usually give everybody bootable SSD with the Linux, where we have everything installed. But generally our exercises, they work both under Linux and under Windows. So we created a set of examples which are compatible with them. Yeah.
For someone completely beginner like me, where to start? How?
Yeah, I will show it in just a moment. But before we start this, I will explain you what this FPGA board is, and what its relation with the chip design in like semiconductor foundry. Because such boards are used to train people who create fixed mass produced chips. You see, so for like every person who worked like Samsung, Nvidia, Apple, who do design, at some moment in their like young age, they had labs with FPGA boards, because this is the way how such a designer can be trained. So now, yeah. So yeah, and so basically every student is getting this component and just connect like 5 wires and connect a display and start doing exercises. So now let me show you kind of basic idea what we are talking about. So in the deep past, when people designed first computers, so first computers were with like vacuum tubes and with like individual transistors, and then the first microprocessors appear around like year 1970. But originally they were just like drawing things on the board, and even designers of chips in 70s, like a Z80 chip, were just using like pencil to draw things on a paper. Then they started to use it late 70s software to like enter schematics, and they can do automatic place and route. But they found that there are some limits of how much design you can do in this way. So in 1988, a new methodology was invented, which we use until now. So, and the industry very quickly adopted it around year 1993. So in like early 90s, it was adopted. And this methodology is called hardware design language based design on register transfer level. So what actually happened with this methodology is that instead of drawing individual transistors or schematics, you describe with the code. And here you can see a code in a Verilog hardware description language, which actually becomes this transistors. So this is different from a software code. So if you write something in programming language, like if you write something in C, you get this code, and this code is translated into sequence of instructions. So you get like a program in C, you have some loops, you get functions, and this all become a chain of hexadecimal instructions stored in a memory. So this is essentially how like software works since the invention of von Neumann computer in like mid 40s. But with hardware, this code becomes hardware itself. This becomes this code becomes a graph of logical elements, and then a mask is produced, which is a file in GDS2 format. This file in GDS2 format is a what like so like basically Applied Materials is making equipment for lithography with those masks. But in order to produce those masks, you first need to design all like areas of semiconductor implanted with like boron, phosphorus, and so on. So and like with like copper wires, so and in order to make this so this is the process which like ends up with GDS2 file, which is used to make a set of masks. Yeah, and this like process it starts from a code like this. So when you have, so what this code is saying? This code is saying that you have a module. Module is a piece of silicon chip, effectively, later on, and you have a signal. You have an input signal for a clock. You have input signal for a reset, and you have 2 wires coming from there. And what this code is saying is that always when your clock changes from 0 to 1. if you have like a reset signal, it sets internal D flip-flop, which is a like elementary storage element. So like 1 bit of memory which keeps its value for 1 clock cycle. So it sets it in 0, and otherwise it uses 2 flip-flops for a counter. So it increments by 1 and counts. So don't worry if you like understand, if you don't understand this thing right now, because you will understand it once you have practical exercise. Yeah, so this is just like a brief overview. Yeah, now when you have some chip, so suppose you have a chip which can be like microcontroller, like a microcontroller used in Arduino, or like a chip inside a cell phone or something like that. So usually in a chip you have a CPU core, you have memory, and you have like other components of a chip. So like blocks that handle different input-output devices. And in such system on a chip, or like application-specific integrated circuit, you have a dualism. So you have a program stored in memory, but you need some block which executes the software. And this block is a CPU core, which is a central processor unit, and this CPU core fetches instructions from memory, the whole stream of instructions one by one, and changes its internal state. So basically, the CPU core is implemented using a hardware description language Verilog, and this is the kind of like essence of why we are here. So we are studying how to implement blocks like this using hardware description language Verilog. Now you may ask question. Okay, so we discussed how you make a chip made on semiconductor foundry, but how is it relevant for us? Because even if we design something, we need to send it to a fab and wait for like a half a year before we get it back. But we want to modify our design to create a product, and we cannot send it like 1,000 times back and forth to the fab. Okay, so now we have several ways how we do design before sending like anything to a fab. So one way is called simulation. When we use software, when we use software that like simulates behavior of our hardware, and so which is effectively like a Verilog language interpreter, similar to like other interpreters, like a Python interpreter, but with just different ordering of events. And second way, but the problem with software simulation is that if you have a large design, like large CPU core, and if you try to simulate it using software, you can simulate small tests very fast. But if you want to simulate something which takes long time, like I mean, the whole 1 second, which is a billion clock cycles of CPU, this 1 second of real time will take you several days if you simulate it in software on register transfer level with a large processor core. So now the question is how to like shrink this several days into at least like a couple of hours. And for this, we are using FPGA, so we are using emulators, so we are using specialized hardware, which behaves in the same way functionally as the final chip, but which has different structures. And FPGA is a special chip which allows us to do such flexible hardware, which allow us to change hardware. So like FPGA, they used for prototyping for education, and also they use sometimes for special applications. Yeah, so like this gentleman uses for medical equipment where he gets a stream of data from some equipment, some sensors. High, yeah, and because the FPGA, unlike like microcontroller, can process the whole stream of data just with a piece of data one coming after another, instead of like doing this in software way, which means that you get another instruction from memories and get from memory other piece of data. So with the CPU, it's more complicated. Now, how does so now how does FPGA look like? So basic idea of FPGA is that FPGA is a matrix of cells, and each cell has a different logic function. So one cell can be AND, and another cell can be OR, and another cell can be NOT. And you essentially build your integrated circuit just like kids build things from a Lego blocks. So you just like connect them all together. But actually, you don't do this manually. You're using synthesis software. So using the same very software used for fixed chips, but you use the software to make configuration inside FPGA. And um, uh, uh, so I will not explain in details how like inside the FPGA how like it works. So I will explain once you go through more exercises. But just uh, just like I want to tell that whatever you can do on a silicon foundry, you can make in FPGA, but with FPGA you have more limited resources and they are not efficient in terms of timing. So like the same CPU which in ASIC may run with like 2 gigahertz frequency, we run in FPGA for like 20 megahertz. So much, but this is still good enough for like prototyping. And same thing, like people in large electronic companies, so in like Intel, AMD, in something high, yeah, just come here. So in like Samsung, like in Apple, yeah, just like sit down here. So using yeah, so you don't have to sit here. So use FPGA to prototype future CPU. So basically they have the whole box filled with FPGA, and this box costs like several $1 million. And then they prototype first CPU in such box, and then they send order to the fab. Yeah. So now let's go basically back to slides explaining beginning of this technology. Okay. So this is kind of idea of what we are doing here. So you like understand mainly concept. So there is some flow which was created for design engineers, which allow to manufacture chips on the fab. But FPGA allow us to make prototypes of small circuit on the table. So while we are working, and this is the way how people are trained to become chip design engineers for like chips and like smartphones and like AI accelerators and so on. So now what we are going to do is that I will tell a little bit more theory, but then we are going to get a bunch of bunch of boards and make exercises with those boards. So just I will get a thing from another, yeah, from this set. We will do a bunch of exercises with the boards. Yeah, so okay, so this student, he actually met with me already on like Maker Faire, and he did some like simple exercises. So like I will show you how to do simple exercises. Yeah, but for you, I have actually a special project. What I want you to do, if you're like interested. So what I want you to do is that so like we have so we have such like simple like set, and I have some like extra computers, so you can use. But let's also talk with other people. So and like for you, I have actually special projects which you can. Just a second, let me find it. Which actually also started in a Maker Faire. But I put it somewhere here. Just a second. This was in my hands. Yeah, but while like I'm looking for it, so maybe you can tell. So did you try to learn something about this like basics of RTL design or uh, uh, FPGA on your own? So like did you try it like in last like 2 weeks? This is fine. Yeah, because we are start to do this today, but. Yeah, but did he? No, my main question was whether he tried to learn something on his own or not. But if he didn't, this is fine because we will now learn it anyway. Yeah. Yeah. Okay. So basically, in addition to those exercises we did before, yeah, I can actually give you a laptop instead of this, so you can bring a computer here. But let me just show you a good project. So last year, so 1 year ago, I went to Maker Faire, and there was a guy who was selling devices that measure radioactive particles. So this one, so this is like a Geiger tube. Yeah, so they actually register radioactive particles from space, and you can. And I have a little bit of uranium salt, which actually creates particles. And we can, yeah, this is used for like school, so this is safe. But this just creates a bunch of particles, so we can test. So usually it's like register just a few particles a minute, but this thing actually creates the whole stream of particles, so we can like test it. Yeah, and basically I have a demo. And that guy, he is actually a senior director in NVIDIA, but he was going to Maker Faire and selling such devices for like school kind of projects. And he was connecting this to like Arduino or to like Raspberry Pi. But I connected with the FPGA board, but not with this one, but with a different board. So let me show you board I connected it to. Yeah, so I was connecting it to this board, but and I created a module which actually registers those particles. So I can show example on this board. And first I show example on this board, but then but then I want you to connect this board with the two pins here. I will show you which pins, and then copy module from example for that board and make this like a particle thing work with this board. Yeah. So, but not only that. So usually. So usually, yeah, so you can just put it as a shell, yeah. So usually what I found, what is like really of beneficial to school students, if he can also document it, so create like slides in like a Google slide to show all steps and how this all works, and make it in the format of presentation, yeah. And then like and maybe make some like a little articles or some like a text site, and basically this is very useful because later on you can send link to this senior director in NVIDIA and show that like, look, I like documented how I created this like project here. So this is very useful because you see he can give some like reference to universities and so on. So yeah, and I will show you demo of this thing with this board, and then you can just move some code around and create, understand how it works, like understand how code inside this like Geiger particle module works, explains it all in slides, and maybe also read some material from the site this like NVIDIA person created. Yeah, but so let me work with you on this thing. But before we do this, I will show some more basic exercises. Yeah. Okay. So and okay, so like for you, you need to connect this computer, yeah. Then you will need to follow. Um, so first, let me give you instruction how to connect those wires. So I will test on you instructions because we actually plan to do several seminars. So right now you have some professor from Mexico on the call, and they will test on you the same instructions I'm giving to them. So this instruction how to connect wires, and let me give you instruction how to run examples. Yeah, and this is instruction how to run examples. And once you connect and run example, we will do some exercises with the graphics. So we will draw graphic pictures on the screen. So let me give a little bit of theory before we start doing something practical, so that you will understand like practical things a little bit better. Yeah, but before we start this, so we have a couple of new people. So maybe you can tell about yourself. So yeah, what is your name?
My name's Logan.
Uh-huh.
This is my first Verilog event I've come to learn, but I've studied computer architecture and built my own computers and CPUs in the past.
Ah, okay. So, but what technology did you use to build CPUs?
I've built like a breadboard computer.
Ah, okay. Using small scale integration, like CMOS 4000 or which one?
I was using like the 74LS chipset.
Ah, yeah. 70. Yeah, but this is the same thing. So you have just like a four nans or D flip flop, something like that, right?
Yeah, I'm good with logic gates. I haven't used Verilog before, but so
okay, yeah.
my knowledge transfer.
But if you like understand basic concept of gate and flip flop, then it's very easy to go to Verilog. So basically, in all these activities, there are like two major like kind of places what you need to like understand, and like most of like some like barriers people go through. So one like barrier is like understand how to build sequential circuits, and another is how to build microarchitecture objects used in high-performance chips, like pipelines, FIFOs, combine them. But this is like next step. It's like after several months of studying Verilog.
What was the name for the second part?
Second part is the microarchitecture. So basically, you see, overall, if you go to most of universities in the world, most of them these days have introductory logic design classes, like semester class, where they start from gates, flip-flops. Some of them use small-scale integration, and some use simulation, and then going into FPGA board. But usually this class ends with a finite state machine, approximately. So they study like gates, flip-flops, counters, shift registers, and go to finite state machines. And okay, you now like understand basics of computer logic. The problem is that with this understanding, you cannot get a job in like electronic company like Apple or Samsung, because you go to job interview and people ask you about pipeline designs, because this is what CPU and GPU and other such things are doing. And so let me actually show you an example of what this design is and what type of problems are solved there. Because this is example based on like interview questions I asked students who just like graduated. And they actually struggle with it. So you see, like I will be like brief about it, but like basically, and like we have more like next step kind of questions about this thing, or like so. Let me just do it briefly. Wait. Scene projects. Yeah, so like I have it in homework exercises. So with homework exercises, we have it both for introductory and for like advanced people. Yeah. So this is so like person coming to my like interview, and I tell you that suppose you have a block which computes square root, right? And basically it computes square root in 4 clock cycles. So basically you have some like X number at the beginning of this block, and you have square root at the end. No, that's right. You can those slides are public, so you can actually get a link to the slides. It's not a problem. Yeah, this is very like a generic type of problem. And besides, I have tons of such questions. So basically, I'm telling just one question, but I don't ask this question like on interviews now, because I was asking in the past and showing example, and new people ask different questions. So now, suppose you have such a pipeline module which computes square root in 4 clock cycles. So now, suppose you and on the waveforms, it look like this. So you have a clock, and then you like put signal valid, and you put X, and then like after 4 clock cycles, you get square root of X. And then you put like another number, and then you put another number, so you get like a pipeline of things. Okay. Now, so now I start to ask series of questions. So question number 1. So let's compute a sum of 3 square roots, and usually students don't have problems here. So they are saying that let's just put 3 such blocks in parallel with each other, and just put A, B, and C through such blocks, get the result, and like add them. So far, so good. So this is to compute formula, right? Now, now, like basically, if you look to a waveform, you can see what is going on this waveform. You put like stream of data. So you put like A, B, C, and then after number of clock cycles, you get like bunch of square roots, and you like add them, and you get results. So like on every clock cycle, you push into your device 3 new numbers, and then on every clock cycles with some like delay, you are getting the result, right? So okay, so they like do such designs, no problem. But then I asked them another question. So then I asked them questions like, what do you do if you have only one such blocks and they implement finite state machine? But my main question where many of them fail. And just they fail. Some students kind of figure out answer fast. Some take like 10 minutes, which is like normal. But there were people who didn't get it in like more than 1 hour. This is a problem because they were graduating from like top schools. This is a problem because they were not only taught this. So, and the question is that how do you make a pipeline formula for dependency? So practically, if you have a graphics, and if we so basically. Yeah, this Zoom doesn't let me to draw it. Let me stop screen sharing because this when I do screen sharing with graphics, it's for some reason it has okay. Yeah. Okay. So like basically, if you want to create a plus square root b plus square root c. So with such like formula, okay. So now what they are doing. So now what they're doing, they start to show something like this. Wait. Yeah, they start to show something like this. So they put 3 modules. So they first put C, compute square root of C, then they add with B, compute square root with sum, and then they add A. But the problem is that this like doesn't work. So do you see why like it doesn't work? Huh? So this like doesn't work because by the time you compute square root of C, the original B is long gone. So this is simply not on the wire anymore. So if you look to the previous thing, you can see that that if you put A, B, and C, by the time C square is computed here, C, by this time, there is no B1 on the wire anymore. By this time, you have already B4. So like basically all this data is is gone. And then like I asked them like so what are you going to do? And some of them asked that can I have square root combination? So it's only in 1 clock cycle. So no, this would be too easy. Some of them that can we use like Tomasulo algorithm? So like Tomasulo algorithm, this is microarchitectural algorithm for high performance superscalar cores. They study in computer architecture class. But using Tomasulo everywhere is nonsense. It's like digging a little hole instead of shower with like excavator, you know. So and basically answer to this question is so can you give answer, because actually you do have already some basics for like figuring it out.
I mean, I'm having a little trouble following the deck, but
Yeah.
now yeah, I could give that, but I'm not sure.
Yeah, but what like comes to your mind? Yeah.
Yeah, I mean, if the original function is adding 3 square root of, right, getting this up square root.
Yeah, but this is not applicable anymore, because now you have formula with the dependencies. So now you need to compute one first and then add something which is gone already. Yeah, but like, basically it's obvious that you need to store somewhere temporarily this B waiting until C is computed. And then, but the problem is that you cannot store it just in one register, because you have multiple clock cycles, and if you have only one storage, then this storage will be like overwritten next clock cycle. So then what they do is that, so with this like 74 SL series, you have shift registers, right? So basically you need to use your shift registers. So then I asked them whether they studied like shift registers or FIFO or circular buffer in the school, and all of them studied this in like a second, third year, but they just studied it and they don't know how to apply this knowledge. Because basically what you need to do is that you need to do the following structure. There is a shift register, which is essentially a bunch of D flip-flops connected one after another, right? So and they can use to delay B for number of clock cycles. So basically you need to build the following structure to compute such formula. The following structure to compute such formula. So you just put on a side a shift register which delays its value for number of clock cycles. You see, and then when it comes on another side, you add what comes on another side. So this is one way of doing this. But this way is a little bit problematic, because it wastes too much power, for the reason I will not describe right now. So like another way is to use a structure called FIFO, which they also study at school and also study some abstract object, and they don't know how to like use it. And basically FIFO is the region in memory with a pointer. So you have read pointer and you have write pointer, and which like goes in circle. And basically every time you put data into pipeline of square root, you put another data into FIFO, and then every time you're getting result, you're popping from that FIFO. Because accumulator will be overwritten next clock cycle with different data. So suppose you use accumulator. So suppose you are saying that, so you have this like A1, A2, A3, like a B1. So you have like B1, B2, B3, C1, C2, C3, right? So now, so C1, C2, C3. So suppose you start computing for C, and you put B into some like register accumulator, okay? So now it is stored here, and it is waiting for C to finish, okay? But the NC will finish in 4 clock cycles. The problem is that you store B1, but next clock cycle B2 is coming. What are you going to do with the B2? You cannot store it into accumulator because then you're losing B1. Okay, so you need to have multiple storage places. And now the question is whether we organize multiple storage places using shift register, using circular buffer, using FIFO. This is like details. The most important part is that we need to store them somewhere. And this is what apparently students, and actually they have all this information in their textbook. They just are not trained by professor with practical exercises. And that's why then they fail interview. So like basically, if you just get a bunch of such exercises and train with like simulation and FPGA boards, then person can do it much easier. Yeah, this is like second place. So like one place is to somehow walk through is with stuff you know like already, with like a function of D flip-flop and what it does. And second is how to build such computing structure. And actually you can build such structures not in abstract way. There is a new book which is coming in January, and a professor who wrote that book actually gave me that book for review. This book is called this book is how to build the CPU, like open source CPU called Volley, which now exists as a like project in a GitHub. So let me close all this thing, and so and let me open. Second. Yeah. So you see, this is like a book with a CPU, and it has like a floating point unit. So we can actually get actual blocks from a actual CPU capable of running Linux with a different latency, and combine blocks from here in like our exercises. So you see, this suddenly becomes not a simply interview question, but like interview question with the real industrial blocks. Now, this book is going to be published in January. But code is already in a GitHub. So if you go in GitHub to so this is called Open Hardware. So this is Valley is a configurable RISC-V processor. So here, Open Hardware Group. So David Harris is like author of several textbooks. So you can see that code is here. So like basically all you need to construct such a custom computing blocks, and you build your own supercomputer by you just go here, you click on source, then you go to FPU, and then you click on like square root. This is multi clock cycle square root, and they have like multiple stages for square root, or you go to like multiply add, so you can see how multiply add looks inside. So this is a block which has this some like mantissa exponent, sine, like everything here. So you have in, you have out, and you have Verilog. So this is just a one stage. This is for addition. So now for so this is add multiply unit. So which is actually a combination here, but they have like square root sequential.
So it's a CPU with a floating point unit.
Yeah, this is a CPU with a floating point unit. So you can have a sub block. You can combine those sub block and make like homework exercises. And if you do such like homework exercises, you can train students who can actually then pass job interviews. Because
Finding like with the working side, difficult logic that is large. What infrastructure do you provide debugging this code when you make a slight change, something doesn't work?
yeah, basically the best things to debug is to use Synopsys Verdi or Cadence SimVision, but those are professional tools which cost like several tens of $1,000s. And usually Synopsys and Cadence, they license them for free to universities. So so you can use tool like a free version of Questa, but it's less convenient. And there is one more simulator which I didn't try, but we can use just Icarus a simulator and waveforms with there is a new waveform viewer which I didn't show yet. It's called I will find it's like what but anyway, you just debug this with the waveform. You look to waveform and you see signal changes. And then when you have a PGA board, you can run like large number of things. Yeah. So now let's go back to simple exercises. Yeah. So now one. No, this is a similar board. Yeah, this is this one. Yeah. If you want to see different board while we are talking about different things, you can go to the box. They have large collection of boards. To this box. Yeah. So feel free to browse through like all of them. Just make sure to keep them in one place, because then I have to put them back in this box. Yeah. And now, you can like open and see what is inside. They're not very fragile. Yeah. So now, what we do to train in basic exercises. So let me get such set, and I will show you what to do with the set, and then I want you to replicate what I'm doing. Because this is the kind of exercises we are doing with beginners the first day. So first what you do is that I can actually show like even the very simplified way of doing this. So you just get this screen. So let's not connect this device. Let's connect just a board with a screen, because we still have So let's start. Let me give you the thing as well. But let me just show you how like it works with just a board and this thing, and then we do something else. So so you just connect screen to this little board, and then you connect this to a computer. Yeah, you can actually come near here, and you can see like what I'm doing. Yeah. So I like so you can like all of you can So you can all come here and just see it on this like little screen. Yeah. Yeah. Okay. So what you do is that you just connect it here. So you don't try to put like anything else. So you just yeah. So first you need to put this up, then you need to put inside, and then you put it down. Let me show you. Okay. So you put it like here, and then you latch it. Yeah. Then you latch it. Yeah. So let me give you the same set. So we all do such.
Like you watch, I would.
Oh, okay. That's fine. Yeah. So okay. So now now what we do is that we usually I like students to use Microsoft VS Code, because many people know how to use Microsoft VS Code. So let me close this thing. Yeah, so you just start like VS Code, and yeah, let me close this one. Yeah, so like in this VS Code, let me just make it larger. Yeah, so what you do with the VS Code, you start so what we have here is that we create a design. We create a design which has a graphics controller. So let me draw it on the screen. I need to stop sharing and then in graphics. So essentially we created a design. Yeah. So we have a block which is a graphics controller. So we have some like module which has a graphics controller, and here is your like user module. And this like graphics controller, it gives you coordinates on the screen, X and Y. Okay. And then it forms all the signal necessary for this LCD display, and you don't need to worry about those signals, because what you need to do, you need to create red, green, and blue for this coordinates. So you create RGB, so red, green, and blue based on this coordinate. So you can use a combinational logic to create it, and in this way you get static image. But if you want to make moving image, you add sequential logic. And this is how you create a moving image. So now what I do as a very first exercise, so I will just try to do this faster. Yeah, let me share the screen again. So basically, when you start first exercise, like I just said, let's draw a red rectangle on the screen. So in order to draw a red rectangle on the screen, yeah, let me actually give you. I will see if I have another laptop. No. Yeah, you can actually get a display from there, and also keyboard and mouse. So they have display, keyboard, and mouse, and you can connect it here. No. So you also put here VS Code, right? Yeah, I put here. Yeah. So let me show you where they have displays. Keyboard. So, hey, yeah. Yeah, so you just choose some display which has HDMI here. For example, this one. Yeah, so you can get this display, you can choose one mouse and one keyboard and just connect it. Yeah. Mhm. Yeah, so now let's so now what you do, you like open basic graphic music. So did you like open that project already or not? Let's see. Yeah, okay, yeah. So you actually programmed this already, okay. But you programmed, yeah, and you programmed this, yeah. So this already worked, right?
It was like that.
Ah, it was like that. Okay. So what you do is that you go to let's go to this Maker Faire, and you can see here the very first example. So which is here, which is like draws red rectangle. So it creates combination logic that if x is more than 100, x is less than 150. So what you do is that you use right mouse button, put open in integrated terminal. Okay, and now here, what you do is that you need to do bash synthesize for FPGA. So now it's running a program which converts this code into configuration in FPGA chip. Yeah, so now let's put here S because I don't think flash works. Okay.
So
Yeah, so see it draws here red rectangle.
I understand correctly, Yuri. So
Mhm.
so the output is just to draw this red rectangle.
So basically we are building piece of hardware which accepts X
Okay.
and produces color. And this piece of hardware is formulated as a configuration file for this chip. And then we put this configuration from computer to this chip. And now we have here a circuit which is getting coordinates and makes a color on this display. Yeah, and you basically you start from if you need chords, they have extra chords. So they have some extra chords over there. So you need to connect this with a cord. So you find extension. Do you have another extension code? No. Ah, yeah. So you have extension. Yeah. So you have this extension cord. Let's see, and they have a bunch of extension cords there. Ah, yeah, and also this one. So you just connected them.
So let's say.
Okay, so you know how to run it. So
There you go.
ah
Talking with him on this example.
mhm. So which example? A floating point?
We're talking about how this works. I'm learning, but I don't. If I can, I'm gonna follow.
So we need to start with like Verilog basics. Because he just
Yeah. So now I will give some theory about Verilog as a language, but let me start. Yeah, I will talk about such theory right now. Yeah. Okay. So okay. So now, slow down. Yeah, it's okay. It's not very fragile. So yeah. Okay. So now. Uh, so now let me just show like important thing here. So this is a demo of history. Demo. Zero, five. So we run here GUI.
I don't think about the Verilog, like syntax, Verilog, like somebody, like sequence.
So like if you run, if you run here a script called run GUI, so you can do here ls, and then you can run a script called. Then you can run a script run GUI for FPGA synthesis. So to run this script, so what you do is that you do bash and then 05. Yeah, run GUI for FPGA synthesis. Yeah, and now what you do is that you go to tools and you go to schematic viewer, you go to RTL design viewer, and then it shows you what kind of schematics it produces. So you need to go here and you need to magnify it. Oh, here's magnification. Yeah, so you are getting this user module here. So you're going to here to laptop. Yeah, and here you can put this plus. Then you put here. Yeah, so you can see that. Yeah, so here you put a comparator. So this shows schematics for this rectangle.
Right.
Yeah. So you see, so your code produces such schematics. This schematic becomes a configuration file, which is used to configure this FPGA.
Okay. Wow.
Yeah, you see. So this is, yeah. Mhm. One second. Yeah. Okay. So now, okay, good. So now what we. So now let me tell just a couple of words about syntax, about theory about syntax. Then I will show him demo with this radiation sync, and show how to connect the pins to measure particles. Yeah, and then we will spend some more time on this thing. So now, yeah, password is a Verilog. So same thing as username. Okay, so now let's show a couple of words of theory. Second. Yeah, so in hardware in generally you have two type of logic. So one is combinational logic, another is sequential logic, and you know this well from exercises with small scale integration. So with a combinational logic, syntax is a very simple. I mean, like, it's not simple, but it's basically very simple. So you start with a module, so you write a module and module. And then you have input, so you have input via A, B, C, D. Okay? And you have output via E, F. So in order to create this circuit, you just write assign E equal A and B or C, and F equal not C or D. Done. And it creates such circuit. Okay. Now next thing, but you cannot do much interesting with combinational logic because you cannot repeat action, store state. So you have sequential logic. Now, yeah. So those are so now you can create temporary objects called wires. You can do assignments. You can do multiplexer with this assign y is equal if. So multiplexer is a hardware if, and there is small scale integration. Yeah. Mhm. Now, huh?
1, 0.
Yeah, this means that there are multiple bits. There are 2 bits. Bits from bit 1 to bit 0. If you put here from 7 to 0, this means 8 bits from bits 7, 6, and so on. So you are now operating with the buses. Yeah. And now you also have a construct called always block, and it's usually written as always comp, but here I'm using all the syntax, which is always at start, and you can use some programming language like constructs here. And I have a set of examples called system Verilog exercises, system Verilog homework, and you can learn all the syntax going through those exercises. So this is on website, but combinational logic is not enough. And in additional to combinational logic, you have to have sequential. Why? Because if you have combinational logic, because this is not abstract world that we live in real physical world, things do not happen instantaneously. Things have a physical delay called propagation delay. So if you start changing voltage on A and it goes from 0 to 1, then in order to propagate this change through this logic element, you need some number of picoseconds, like 50 or 20 picoseconds. So it needs to propagate. So basically your formula will be computed after a certain number of picoseconds. Okay. Now the question is when. And when we are using a tool called static timing analysis, yeah, you see there is a delay between input and output. And the problem is that it's not clean change. It just starts to change and goes through some like time when it's kind of not defined, and finally it goes to stable state again. So it needs to go from stable state to stable state. Okay. Now, in order to now eventually all logic changes will go to stable value. And now the question is that how can you measure time when this moment occurs? In order to measure this time, you have special signal called clock. Yeah. So okay. So oh, you don't have internet here. You can just put here, but it doesn't matter. You don't really need internet. I will show you in just a moment how to work with this board. Let me first put this board and show example with this board, and then we show what to do with this board. But anyway, let me just finish with him quickly. So basically, in order to do this, you need to use special object called D flip-flop, and we need to like introduce concept of clock. So clock is just a periodic signal which goes up and down with certain frequency, and we need to use this signal in order to find where a result of computation is ready to be recorded somewhere. And on our boards, we have a chip called crystal oscillator, which generates such clock signal. And on some boards, it is 50 megahertz. On some other boards, it's 27. And then we can use special block called PLL to make some custom frequency. Now, we have a crucial element, which is called D flip-flop, which is a storage element for 1 bit in 1 clock cycle. And basically, the function of this element is that this is written in this way, that always at positive edge of clock, so when clock changes from 0 to 1, then store input in the internal state. So always block is just a syntax construct that always when something happens, do something. So here is that always when clock goes through positive edge, so always when clock signal changes from 0 to 1, then record your input D into internal storage queue and connect this internal storage to the output. Yes. So now next thing, you can have a reset, and then you can have a buses with a parameterizable width. I don't want to go through details of syntax. So finally, in this block, if this is input like 0, 1, 2, 3, and so on, this D flip-flop will recorded only when clock goes from 0 to 1 and keep it for the whole clock cycle. Okay. Now, if you have 2 clock cycles, you have delayed by 1 more. If you have 2 D flip-flops, you have delay by 1 more clock cycle, and so on. And now, if you combine combinational logic with registers, you get circuits like a counters.
Question?
Yeah.
The way you draw the circuits, that's equivalent to the Verilog code, or when you add only block. How does that affect the way you draw the circuit?
Always block is just tells us when we record whatever we computed into storage element. Yeah, but let's not go through this now because shows graphically synthesis tool infers, so it understands what this code does, and it infers, which means that create hardware structure which does specified action.
Structure, when you say take this Verilog drawer as a circuit, it doesn't change that at all.
No, it just that particular viewer. Yeah. So let me just show this like animation. I will go back to this example. So now, if you have a register which has 2 flip-flops, which has 2 basic storage elements, and we have adder, we have a block called the counter. So here in storage element, we first have 0, 0, so 2-bit number, 0, 0. And now we have the 0, and we have 0 coming to the output. And this 0 is propagated to an input of an adder, which adds it with 1. So now the 0 travels here, and 1 plus 0 after number of picoseconds become 1. But this one is not recorded into storage element because clock didn't come yet. Okay. Now we are waiting until clock come, and then clock comes, and this is time of so-called aperture or write time. We are saying that now, when this moment happens, we write 1 into a storage element. Okay. Now we put it 1, and then like it just stays there, and then we put 1 to output, and like at this moment, the input to this adder became undefined, so it goes through time of changes, and then we propagate this 1 to the input of this adder, and then we add 1 plus 1, and it becomes 2. But this 2 is sitting there, it's stable value, but it's not written into D flip-flops yet, because positive edge didn't come yet. So now positive edge, so negative edge, it's negative edge. Oh, you mean in that code? You're talking about this one. This is the negative edge when reset goes from 1 to 0. There are so-called negative edge flip-flop. Negative edge flip-flop means that it writes not when clock goes from 0 to 1, but when clock goes from 1 to 0.
But in the flip-flop, the other, but the clock negative edge.
Yeah, clock negative edge is when clock goes from 1 to 0. So let me show you on diagram of clock. So see here is here's positive edge. Oh, sorry. So here is a positive edge when goes from 0 to 1. Here's a negative edge. Negative edge is what goes from 1 to 0. So clock goes up and down. Up is positive edge, and here is a negative edge. So positive means it goes from 0 to high to plus. Negative edge it goes from high to 0.
What's the other thing?
Uh-huh.
The other thing. With the other.
Yeah. Let's go to other. Yeah, here. Uh-huh. When a negative edge happen, nothing happen. So negative edge is ignored by positive edge flip flop.
Go forward.
Uh-huh.
Go forward.
Yeah. Okay. You are going for okay.
Forward. Forward.
Yeah. So this is positive. Uh-huh.
It says the positive edge right here.
Yeah.
Forward.
Mhm.
There's no mention of negative.
Yeah, because negative edge we just ignore here. Nothing happened during negative edge. No. On a negative edge happened, but flip flop ignores negative edge signal. So like you can use negative edge, but not in this example design. So we can use negative edge in like other designs. In fact, there is one interesting interview question: how to produce a signal using both positive and negative edge flip flops. But this is not our case yet. Here we use only positive edge, and on positive edge we write, and on negative edge we do nothing. On negative edge we just keep whatever was there.
When is the negative edge in these slides though?
Huh?
In these slides, when?
Oh, in this slide we don't show negative edge. Negative edge just happen sometimes during this time, but we don't have special slide for it. So we show only positive edge coming, we never show negative edge. You see? We can add additional slides, but nothing happen when negative edge is coming. Yeah. Okay.
So there's between the output and the flip flop, it probably takes a few picoseconds to add together one.
Yeah.
But there's no circuitry stopping like the input signal change. And
The input signal will change, but be ignored until positive edge comes.
but like the I know it's on the edge, but in reality it takes like it's going to be reading.
Yeah. No. Yeah, this is called aperture. So let me show what is physical reality. Good. But anyway, when we put 1 plus 1, it becomes 2. Then we positive edge come, we record 2. Then 2 is coming. Finally, we are having this type of animation. This is how we produce new number every clock cycle. Now, like answering your question. So if you go into like textbook description of this thing, the description is actually much more complicated. When you go into details, you're just going to like abstraction level where we don't look for details. But just when logic design engineer designs this thing, he usually doesn't think about it, because there is physical design engineer who will tell that you have a problem. Now, but what happened in a real, if you go down to all the details, so what happened is you have so in a reality. In a reality, clock has so-called slew, which means that it is not going directly to which means that like voltage does not go directly from like 0 to whatever high is. So now high is like around like 1 volt to even 0.8. But for such for these boards it's usually 3.3 or 1.8 volt. But let's say this is like 1 volt. So clock does not go straight there. So now you and in addition, if the clock is not propagated in all areas of chips at the same time, so you have also skew. So this clock itself may appear in some areas of chip a little bit later than like in other areas of chip. So, but basically, what you have to have with the physical level, there is a time period called aperture. And this time period called aperture, it's a time before and after this change. And during this time, signals shouldn't change. Signals should stay stable. So signals must stay stable during aperture time. So basically, all interesting actions with signal should be in this area. So in this area, it can fluctuate and even go into a state which is not 0, not 1, in so-called prohibited zone. But eventually, it should go to either 1 or 0. And by the time of this aperture, it should become stable. And then it's written into flip-flop.
So the technical term.
Yeah, this is called prohibited state. So this is the technical. 1 second. It's I so this is what is this? This is prohibited. What's it? Is it prohibited or state voltage? Prohibited state voltage. So let me show you textbook about this. This is no. Oh yeah, this is like a VLSI. But anyway, let me show this in Harris textbook, because this is like first chapter of this textbook. Just a moment, I need to find it. So I have here projects, texts, download documents. I think it's this one. Oh yeah, here. So let me show you from this book lecture slides. This is on a very first lecture. Yeah, from 0 to 1. So it has binary numbers, hexadecimal numbers, addition. Logic. Yeah, here is a. So we have logic levels 0 and 1, and so we have noise. Yeah. So this is called forbidden zone. Sorry, this is the right term. So it's called forbidden zone. Yeah. So this voltage. So but between positive edges, voltage can go into this forbidden zone. Now, what happens if our design has too much logic and it doesn't fit in clock cycle? And suppose the signal in this forbidden zone. This signal will be written in flip-flop during aperture, and you will have thing called metastable state. And metastable state, it means that it goes into state which will be resolved eventually, but it can introduce very bad bugs in your design. And usually, like in order to remove metastable state, so this is the whole separate topic. You need to put additional flip-flops to make it statistically resolve, and like in the Cairo chip where we have many D flip-flops in telephones, we usually synchronize it with like 3 flip-flops because if you put 3 flip-flops, probability of going into metastable state logic after this is the mathematical expectancy of fault is more than like age of universe, and this is what you need to have. Much more than age of universe, because you have those like hundreds of millions of flip-flops in your design. You need to multiply by, divide this expected time by this to make sure that it doesn't fail. But in a commercial product, this does fail once several years, which is okay. If like your phone suddenly doesn't work, but for medical equipment and for they have much higher standards for it to make sure that it doesn't fail like during the like life of universe. Yeah, but anyway, back to my slides because I want to finish this and go to this radiation example. So basically, if you go here, you can see this is basic principle of sequential logic, and the generalization, this is the Huffman model of sequential circuits. So every hardware design you can represent as inputs, outputs, as combinational cloud, and as clock and state registers. And so basically, yeah, you can build finite state machine here. Here goes into finite state machine, but this is like next thing, and some books about it. Now, so now, if we, yeah, so now, if you want to learn syntax of system Verilog, what I recommend to do to go through exercises called system Verilog homework. So if you go to GitHub, I have a repository called system Verilog homework. So what you do here is that you just clone it, and then you install a tool called Icarus Verilog, which is a Verilog simulator. And then what you do is that you run only one script, which is run Linux, Mac, or run Windows. And and then you go through a bunch of simple exercises. So what do you have to do with such exercise? You need to go to, so this starts from simple questions. So suppose you have a multiplexer which chooses from 2 numbers, D0 and D1. Now write a multiplexer which chooses from 4 numbers. Now if you don't write anything, or if this is not correct, so like if you write everything, so like if you run this script, it will tell you pass for all exercise. But if you have homework without solutions and you run the script, it will just tell you like everything failed. So basically your goal is to make all these exercises pass. And this starts from like elementary exercises, but it goes to like exercises on like a job interview level. Like even at the end of first chapter, it does have exercises that are used by companies to screen people, but because everybody knows this question already, now like other questions are used. So if you go through all those exercises in parallel with reading like a couple of books, then you will learn syntax. Yeah. Now one problem is that in the schools they actually don't watch it very carefully, and there are even So this is one book. So let me show you a couple of books, and those are two more books what you can use. But to learn syntax, I recommend this two books. This like Harris and Harris. Yeah, let's put it here. Yeah, so Harris and Harris and sorry. Yes, and this one. Then you can also add this book, but this book is used as the main textbook in Stanford. So this is a good book, which like one of the best books, but this is not a kind of perfect one.
It's just not about Verilog syntax or
This is about both of them. This is both design. So this book is mostly basics of both design and Verilog. This has chapter 4 about Verilog, another chapters about digital design. This is mostly concentrated on language, but it shows other things as well. Yeah. Okay. So this is basically serious. Now let me show you how this thing works. Yeah. So let's run this particle thing, and I will show you. Oh, wait a second. Was there any other chord in this thing? Yeah. Oh, yeah. Here. Okay. So let's disconnect this one, and I will show you the thing in action. Then we need to connect this thing to like another board. So yeah, this is actually easy task. So you can do it, but then there is a little bit more complicated task because I want you to put this in bunch of presentations. Okay, so you connect it here, and now let me see where is the example for this thing. 1 second. So this is supposed to be boards, labs, unfinished. You are round the robin. I missed. Yeah, it's a Geiger. Okay, so let me make sure that this thing actually works. Geiger input row, GPU +1. Okay, let's see. So let's go to VS Code. So where is the mouse? Let me. Let's go to VS Code. Now let's go down. So let's minimize this in graphics. Minimize. Go to the miscellaneous. No. Go down. Yeah, miscellaneous. Yeah. This has Geiger, Mueller. Yeah. Okay. So now here with the right mouse button. Here with the right mouse button, put open in integrated terminal. Okay. Now here. /06 tab. Yeah. Okay. Enter. Yes. Enter. Now put this window. Get this mouse and just put this window up so you can see the whole menu. Yeah. Move this thing up. Okay. Now go here. Go here. Yeah. So we need to set board called D10 light, which is number 16. Yeah, so put 16. Yeah, okay, enter. Okay. Now put ./03. Yeah, no, ./03 tab. Yeah, okay, let's synthesis. Yeah, run it. Okay, so now if this doesn't work, we use another version of a repository because I didn't update it for a long time. But let's see. Maybe it works just right away. Oh, right. Yeah, you see particles. We have a lot of radioactive particles here. All right, let's give it some more particles. So you see, we are putting this. Uh-huh. Uh-huh. Radiation. You see? Yeah. Yeah. So now it gets only cosmic particles on some like background. But if you put this like radioactive salts, it actually makes immediately it goes like crazy because it gets more particles.
Between the two tubes.
Actually, we are here we are using only one tube, but if you use two tubes, we can make some more interesting exercise like a direction of particles and so on. Yeah, this actually for you to figure out because I made very basic exercise. You can even estimate energy of the particle in but in a complicated way by computing how by computing how fast it goes down or something.
So
Like
you change the voltage on the tube, or
actually, I'm here using only like only two bits, one bit from one tube and another one bit from another tube. But I have a pulse, so I can compute width of this pulse. You see? And by computing width of this pulse, we can some like indirectly do some like estimation. Yeah, but I didn't do this. Yeah, maybe you can actually explain to him because you're a physicist and I'm not. So
I would
yeah.
be careful. There's probably 100 volts at least on that tube.
Yeah, okay. Yeah, but 100 volts, it's okay. In my childhood, I was hit by 220 many times.
Yeah,
Not a problem. Yeah,
it's not a lot of current.
yeah, yeah. Certainly, it's not a good idea to drop it and so. Now, let me show you how code looks like. Because okay, so basically, what I want to do, I want to do the whole project, like, and go to some like non like trivial area. So, so first of all, I want you to figure out how to connect it to this board, because this board has like extra pins we are not using. All you need to do is that you need to use a couple of wires to connect, like disconnect this one. So you just disconnect, and then you find here the right wire and connect to wires here. This is like one thing. But then, so let me, yeah, this like thing you can figure out by yourself, but you need to look around very carefully. So now let me give you wires for this. It was like $60 or something, so something like this. So from 50 to like 80. So he is the guy who is selling it. So uh, he works. He's the director of NVIDIA. So Haber. Yeah. So those are wires to connect to here. No. Yeah. So this is the guy. Yeah. So his website is called GGLA. Just a second. I will find it. Um, okay, GGL, let's see, GGL, GG Lab, yeah, it's called a GG Lab. Yeah, GG Lab, just a second, GG Lab, 1 second, GG Lab, oh, yeah, this one. It's called GGLab US. It's got some, yeah, so here is the GGLab US. So here is some safety certificate. But anyway, yeah, so he is like selling it here. Okay, let's see what is the price for. Yeah, so here is a board. So one thing that you need to look to schematics of this board, and you need to figure out the right pin to use. But actually, you can see pin in the code. So now let's go do some like code review here. So what we are doing here. So first of all, what if you go into miscellaneous, yeah. So if you go here, you can see that that in order to connect to this board, we're using 2 wires using signal called GPIO, a general purpose input output. Okay. So and we are calculating it using this expression. So GPIO base plus 2. So what is the GPIO base is 36. I need to turn off screen sharing because it's what happened with this poor computer? I opened too many windows together with screen sharing. Opa. Sometimes Zoom with screen sharing does such things. Okay. So just Zoom hangs. Okay, good. Okay. Close. Okay, so let's yeah, so Visual Studio closed. Okay. Now let's do some code review. Let me close everything unnecessary. Okay, so first of all, okay, does it do recording? Yeah, it does. Okay, so first of all, you can see that First of all, in order to do this, you generally need to learn a little bit Verilog syntax. So to learn syntax, you need to do system Verilog homework exercises. But anyway, so this syntax means that we are getting signal from GPIO, which starts from signal 36 plus 2, which is 38, and it uses two bulbs. So this signal is here. It's a general purpose input-output signals. Now this GPIO signal in those two boards is different. And this is the trickiest part. So you may need to change this code and make it dependent on a specific board. So right now you can just use like GPIO as some constant, like GPIO 0, GPIO 1. Now this laptop module is instantiated in a module D10 light board specific top. So this board specific top has this series of pins called the Arduino IO. And because the thing uses Arduino Shield, we have this in-out port called Arduino IO. So this Arduino IO has a reset, and we need to connect our reset port to it, and we are putting Arduino IO to this GPIO. So we need to hook up external pins to your module. So once you hook up external pins to your module, then like everything else is easy. Yeah, I can help you to do this like hookup, because this is kind of less trivial operation. So what we need to do? Okay, so here is our. So here is our configuration board specific top. So here GPIO signal. So how much time we have? Half an hour. Okay. So here we need to use one of GPIO signals. Okay, and where is this picture which GPIO signal is available? Yeah, here is a picture. No, that, yeah. So if you get this thing, you can see signal GPIO 3 and GPIO 4. So here GPIO 3 and GPIO 4. So effectively, what you need to do to make this work, you need to go to. Let me actually help you to do this. So you need to go to MISC, and you need to create a lab 6 miscellaneous. So first we need to create a copy of this directory, and we need to call it like 6.1 Geiger Müller radiation counter 10 nano on 10 nano 9K. Yeah. So something like that. Oh wait. You need to create a copy of this directory. Yeah, so first we need to create a copy of this code here. And second, in a laptop, we need to change this line. So instead of GPIO, so you need to put comment. So this is board specific. So this is board specific. So here we need to put GPIO What is the number? Again, this is number 34. Yeah, so we need to put GPIO 43. Or we can, no, not like this. We need to change the GPIO base. So our GPIO base is 3. So we need to put here 3. Yeah, so this is where we start GPIO. So we need to put here 3 and make a comment that 3 is for 10 nano 9K, but 36 is for Jurassic D10 Lite. Done. So now it should work. You just need to hook up wires properly. Okay, so let me check this in. So this is one line you should change, and then it should work in theory. So let me make this. Let me add this to repository. Git add, then git commit. Wait, I need to not to share screen because I want to add a copy of addition counter example. Git push. Okay, now git token. Okay, so now if you do the git pull, you will get this version. So you need to figure out from this picture where wires 3 and 4 are, and connect wires 3 and 4 to appropriate wires on this board. Where is this board? Did I? Yeah. So you need to disconnect. Need to disconnect this thing, and you need to figure out from documentation on GG Lab where the pins are connected, or get this from. So you need to find where the proper pin are, and you also may need to add a 5 volt from here. So here there is a pin with 5 volt, and you also may need to put 5 volts on this board. So you need to figure out how to connect wires from this board to this board. Yeah. So there is a slight chance that you may burn this board by putting 5 volt here, but because this board costs just $16, it's not a big deal. So if you burn it, you just get another one. Yeah, but you need to connect. You need to connect like 5 volts to power these tubes. You may need to connect 3 volts to power interface. You need to connect ground, and you need to connect 2 bits which are coming from two tubes for the pulse. Yeah, so you can just take all this stuff, so all these 2 boards and this board, and try this together. Now, little bit how this works. Yeah, we have to finish soon, but let me show you some basics of how this what this code does, because you may need to like improve it. So what this code does is first it gets the signal. So first it goes the signal. So Geiger input row. Then Oh, and it also assigns LED. Yeah, but these assignments are not important here, so we probably need to comment it in this particular board because we are not using it. So we need to comment applicable for Jurassic D light. Okay, Jurassic D light. So not applicable for Jurassic D light. For Jurassic D light. So we comment out this thing because this is not applicable. And yeah, so first we need to get rid of metastable state, what I was talking about. And we can discuss it later in details because first you need to get some basic training in system Verilog syntax. Then you need to find where pulse starts, so where new level is different from previous level. And this is done in this code. Then you need to count width of this pulse, and you're doing this by code here. And then you add to the counter number of guys. Yes, so basically you need to figure out width of a pulse and count a pulse extension. Like I already forgot why I was doing this. I need to refresh my memory. Okay, okay, extended counter. Yeah, and then I was putting this to LED and then connecting 7-segment display module to display value, which is the particle count. Oh, in this code, I was connecting another 7-segment display, which displayed not only number of pulses, but it displays sum of widths of every pulse. So if you can connect the like second 7-segment display, but it's not that important right now. So you can just check a particle count and not pay attention to particle time count. So here's the particle time count. So this part is not needed. Yeah, but basically we can go through this code. But before we go through this code with you, I want you to read that book and just learn basics of syntax of Verilog, or do some like exercises and connect it to that Vita board. So this is like #1 priority. Yeah. Yeah, this is actually not a simulator. So like I will tell you what it does. This code becomes actually circuit on the board. So yeah, this is the code which become configuration inside this chip. So we have code and it becomes schematic, and then schematic is synthesized into bits in memory which are connected to like multiplexers in this chip and change its function. Yeah. So we program this chip, yeah, and then we need to, yeah, this board does have controller already, and it generates 2 signals. Those are interrupt signals. So for microcontrollers, they used as interrupt signals, but we are just using them as signals that particle came. So basically here there are 2 pins, and when a particle is coming, they just produce pulse, which lasts some time. And basically this code, what it does, it just counts how many clock cycles of 50 megahertz clock this pulse lasts.
Just now you're going to batch file. And it actually generates the particles already.
Yeah, what I did, like I run like a batch like script file, which synthesized code and then put configuration into this chip. I mean, like into this chip, and then it starts to run. So this script both does synthesis of the code, plus it configures the chip, and then chip is running. Design of the chip is running. And then this design in the chip get data from this pin, and particles are coming to this tube and generate data on this pin, and this controller gets data on this pin, counts how many clock cycles passed, and then adds a counter and shows here that one more particle came. And it's here counts in a hexadecimal, so not in decimal, but hexadecimal. So you can see it. Yeah, and it also makes.
To what is the goal of this chip?
Yeah, so if you want to put it to this chip, what you need to do is that you need to figure out which two pins from here are sending signal, like about pulse, and then you need to connect it with this wire I gave you, with this wire. So you need to find here proper two pins and connect it to proper two pins here.
Replace this chip with.
Yeah. So if you want to use this board, like instead of this board. Yeah. The reason I'm doing this is that with Jorge, we plan to fly to Tijuana to Mexico to show it to a bunch of students there. And this would be nice demo to make. So that's why the reason I want to make this. But this demo makes actually a good like school project for your son as well. Plus you can make like presentation like about it, show to that guy in NVIDIA, and so like use it somehow. Yeah.
More programmable than the other.
They're both equally programmable, yeah. But in order to make this counter, what else you need to do? You need to connect this part. So did I give you? Yes, I think I gave you this part. Yeah. So this part is there, right? Yeah. So you need to use that part. So you need to put this board and insert it into breadboard, and then you need to use this 7-segment display instead of this 7-segment display. Yeah, so it's kind of a little bit overwhelming right now. Yeah.
Also,
Yeah.
which board is it?
Mhm.
Which board?
Yeah, so this board is called Tank Nano 9K LCD for 08 TM. So this is board number 53. 53. Yeah, TM1638. Yeah, it's kind of overwhelming right now. So, but I don't expect this to be done immediately, because if he wants to do this project, first he needs to read a little bit of Verilog syntax, because he will work with the Verilog code. Then he needs to go to website of this guy and read which pins are connected there.
Like one board, and that's very integrated. So now.
Yeah, so now we want to like integrate this board with this thing. So we want to replace, instead of this board, use this board.
What's the YOFYF then?
Yosis, it's like alternative tool chain. So software to do synthesis. So when we run right now, we are using software which is called Govin EDA, which is a number of programs that compile code into configuration. And Yosis is actually alternative tool chain. The good thing about Yosis is it's compatible with the Macintosh, but the bad thing is that it's kind of buggy, so it's more difficult to work with. Yeah. If you want to read about Govin toolchain, you go to their website. So it's a website of this company. Yeah. So and if you want to read about Yosis, you can read about Yosis. Yeah. Yes. Anyway, But we actually need to wrap up because at 2 o'clock, like another guy is coming and making class here, and yeah, he's coming at 2. Yeah, so we need to somehow like wrap it up. But if you want, you can sit over there, and you can, I mean, like in that room. We need to leave this room, but we can sit over there. So you can actually put everything in the main room. Yeah, like here. Yeah, so you can actually just put everything here, and then like I can show you what can be like other steps. Yeah. Okay. So did you get some basic idea from what? Yeah, okay.
Actually, I know, I know where my gap is. I have an idea of my gap.
Uh-huh.
I look at it.
Yeah, let me actually collect all this stuff and then let me collect all the stuff and then we'll talk about it. Okay. So Timothy, so how are you doing? Yeah, but anyway, I I I need you to so like are you using Telegram? So do you have a Telegram account?
The chat.
Huh?
Have you added me to the chat or not?
Okay, I didn't create new group for sound, but I have like other so but I have like other groups. So which groups are you in right now?
Let me check.
In Telegram.
Just a second.
Yeah, I will read it later on. So we need to form a new group about discussing microphone and stuff. You understand? Okay, I will read you all the necessary groups because I need you to include because we actually making okay, one former Intel employee in Nizhny Novgorod. So they were doing like a parallel computing group in Nizhny Novgorod. So he now like agreed to make a lecture with exercises about sound for their like school of synthesis in Moscow. So he prepare some slides and go to Moscow to do that lecture. And in addition, I also want him to take part in making examples for both microphone and sound output. So I want to create a group which includes you, me, him, and a couple other people who touch this microphone subject.
Yeah.
And then we can discuss how we can improve quality of sound in here.
Yes.
Yeah, this is like important thing. I also wanted something else from you. Okay, just a second. What was it?
I'm likely to skip the next meeting.
Okay.
Just let you know.
Okay. Yeah. So next thing. Uh, next thing, I will also propose a hackathon. Yeah. Yes, I'm working on a hackathon proposal for making games on such things, and I'm working on this like seminar in Mexico and discuss with the maker. Yeah, but anyway, let me put everything wrap up. So if you want, you can move everything to the room and continue.
It was 51 or 53.
So like HDMI, it's when you connect this to like HDMI display. But with this small LCD, you're using 53. Yeah, 53.
Well,
But
I don't have this thing attached.
huh?
I don't have this thing attached.
You just first okay. So first, what you do is that you disconnect this one, and then you put it here. And then you need to just properly attach it here. So to make sure that the power is at the right place. Yeah, let me make sure that it's okay. Let me check it just a second. So oh Wait a second. Uh, we need to change position of these wires. Need to change position of these wires because now position is not correct. Because you see, we need to connect here display. Now position is not correct. Okay. Okay, I need to properly align this thing. Oh, wait, I think it was in different direction. I think it was this way, right? Yes, I think it was this way.
What's the 51 for?
So 51 just means that configuration which has this device and this one. So it's called the Tank Nano 9K LCD, and then screen is 480 by 272, which is this screen. And then thing TM1638,
Yes, but
TM60
there's a
is
no
this
TM
device.
at 1638.
Huh?
There's a no TM.
Yeah, no TM is that when you don't connect this thing and you use only two buttons here and you don't see anything on this 7-segment display. So you want to use TM because you can use TM 7-segment display. Yeah, let me connect it just a moment. I just need to connect and demonstrate you how it works, the 7-segment display. Okay, I think it's okay. I think this is the right pin. Oh, wait. This pin is literally deformed. Okay. Let me I might need to get another eyeglasses. Okay. Okay. Yes, it's connected to the last one. Yeah, let me quickly check on my computer that it works. Huh? Yeah, this is information, yeah. This is information. Yeah. But you may need to do git pull, so can you make a git pull? Is a git pull? Yeah. Oh, wait. Footnote is you need to connect here to the internet. So let's connect to the internet. Yeah, so what you need to do here is that you need to connect to available networks, Hacker Dojo free. Oh, wait. Here is the password is a Hacker Dojo, one word. Hacker Dojo, one word. Okay, so disconnect. Okay, so now what you do is that you go here. This is just to get the latest changes. So you go here, do git pull. Okay. Yeah, but now the problem is that now this menu might be different. So let's see. So now it's not 53, but now it's actually it's a 58 because I added more boards. Yeah, so you need to put 58. Yeah, okay. Okay, good. Now what you do is that you connect this thing here. Yeah, you don't need to connect this right away. I just want to show you how this thing works. Yeah, but you can connect it. Connect it here. Okay. Now, now you connect this thing here. So now let's see whether like TM16. Yeah. So now let's go. Let's see. Yeah. And now this thing is not going to work because you didn't connect pins. But I want to check that something else is working. Let me make sure something with counter is working. Yeah, it's okay. Yeah. So basic, you go to hex counter. So you do here open integrated terminal. Oh, wait. Okay, it doesn't matter. Okay, so now here you synthesize it. I just want to make sure that this 7-segment display is working. Mhm. Yeah, you see? Yeah, so counter is working. Okay, yeah, good. Now, yeah, so now to do next step, you need to research around what pins connected to what, and learn a little bit about that code. So at this moment, I recommend a little bit of reading. So particularly, yeah. So for example, if you get like this book, and if you read like chapter 4, yeah. So you can get this one. Yeah, but this is design which was there before. Yep. But so like if you get this book in chapter 4, you get some more syntax on Verilog. If you want to dig deeper, this is, yeah, let me get, yeah, if you want to dig a little bit deeper, this is another book, yeah. So this is another book, yeah. But one thing what I recommend is look to article on Verilog Meetup website called like self-educating and educating others, and go through system Verilog homework. If you go through homework, through chapter 1 and chapter 2, by yeah, system Verilog homework. If he goes through that thing, by the end of homework 2, he will do basic sequential logic better than most of like graduate students in the USA, like interview. But what?
Talking about your homework repository?
Yeah. Yeah, there's like nothing really difficult there, but the problem is that you need to get this like you know like when you like learn how to play music instrument, you need to play some like a gamma and like etudes and stuff, and the trouble is that many students, they spend time in university. It's like as if you are studying, just watching slides how to press like buttons on flute, and like life histories of composers, but not like actual practice of like playing. So so basically, in such like exercises, they cover this basic practice. Yeah, this is why they're important. Okay, let's actually put everything, because now some like another guy is coming. Yeah, so yeah, you can like grab all this, and you can stay there if you want me to like teach you something. I can be here for some time, or you can just learn by yourself and then come like next time and we will continue. Yep. Huh?
If we come back
Yeah.
home, and which chip that comes.
So what I recommend, you can actually try both this board and that board. You can try both of them. Just have they have different name, but he just need to like explore what I wrote on that website. So learn a little bit of Verilog, play examples with this board, play examples with this board, read on website about this thing, see how pins connected, and then see what he can do as the next step. Because now he needs to learn many like do many like different exercises just to beef up a certain level of expertise when he can easily change such designs. And he can do this like in any order. So he can either start with system Verilog homework, or start reading, or start looking on websites with these boards. It's like up to him. Yeah, just this should be done like in like any order, and after some time, like as I said, the first task is just make sure the thing is runs on that board. And he need to like understand how it runs and what it's doing. Yeah.
You see the LED pin on there?
Huh?
Are you looking at the LED pin? The pin that pulls out, is that what?
Ah, no. It has like special pins which I put into a GPU, general purpose IO pin.
Which pin? I was looking at the schematic, I didn't.
No. There is a interrupt pin on that board with those tubes. There are two like interrupt pins, because when pulse arrive, it just sends interrupt to a microcontroller, but I am using these pins in order to count for a pulse. Yeah, so this is just a pulse when this thing arrive, and width of this pulse is related to the energy of the particle, because how slowly it like goes down. So you can actually make some non-trivial things, and because there are two tubes, you can also count which and figure out the direction of particles.
In Slack, there was a display we had that had multiple, they weren't tubes, they were scintillators.
Oh,
Looked
okay.
alike, same kind of thing, right? And there were directional ones you get, they were like a nuance, or just you get nuance on this probably too. You know, you get probably here you'll just see the betas or whatever from the air. But yeah, it's I don't get energy stuff. We got the two.
Yeah.
You can get the you know, you can figure out your decay constant.
Yeah.
And then from that, you can say, oh, it's whatever. You know, I'd be careful taking that across the board if you're going.
Yeah. Across the board,
Yeah.
yeah, Tijuana, yeah, sure. Yeah, maybe like I will not get a radioactive salt, but just a tube.
Yeah, tell
Yeah,
those
tube
guys
is-
they could buy the thorium, there's old thorium lantern lamps. You can get those maybe in Mexico still.
Yeah.
They're-
Yeah. This is a good idea. Yeah, I shouldn't put this through the border. Yeah.
they should. You never know what it's gonna have. You don't want to mess.
Yeah.
Yeah, 800 by 400 here twice.
Yes, I do. If you want a large display, I can give you a large display. One second, I will find it.
This ribbon cable.
Yeah, so what you so you attach so far so good. So what you do is that you put this to USB port. Yeah. And then you can then you can run it. Yeah, let me give you a larger board.
Are we ending soon?
Yeah. You can actually move there and try it there. So it's up to you. Yeah, but so what system are you using? Is it Windows? So yeah. You can just follow instruction how to install this stuff on Windows and try with this board. Yeah. If you want, I can loan you this board if you will do some like if you like try it, give some like feedback and so on. Yeah. So like I can loan you this set because I have like 20 other sets. Yeah. Just a second, let me give you a big screen. It's in different bug. Yeah, let me exit from here.
I was playing with a very small company. Yep. I'm curious. It's pretty good. The power, but carefully now. Sometimes also some companies very low from the year or some. Okay, so they make it. It's easier to use fire. And we are talking yeah, if you can combine everything and go home, or you can sit there and if you want to do something else, to be here. And if you get some like bags to pack, and I have some additional bags. Okay, well, thanks for that. How about your time? Huh? Thanks for that. You mean board for this one or what? Yeah, so for this one, you are found 909K, then screen size, and then you use scale 60. So this one is 800 by 400 feet. So you need to use 60. For the type of let's see what I do. Yeah, but here, since there is some bug associated with the company, you can make it but it may show some like yeah, you can use the GMX2, which makes sense 2 times larger. Yeah.
All right. This is so fun.
I know two variants of MS.
Huh?
Yeah, they made objects 2 times larger in there's 2 different codes, same thing, but code is different. In variant 2, I just changed scale, so I just made it artificially smaller display. 2 is better, so 1 is slow. Yeah. You guys you hear the first control C, but you can try 1 and you can try 2. I prefer going 2 because the 2 is more.
Okay, now ask me. Oh, Yeah, actually, I do need to commit and push again, because otherwise you will get the error. You need to do full. Yeah, can you do git full again? Can you, yeah, after this, git full again. Oh, but one system. Just git full will not do effect. Yeah, it's just a first, it's how long. And you can actually figure out how to make it even larger or have some additional objects. Yeah, but to add additional objects, you need to learn more value. Yeah, okay, let me put everything, I'm sorry. So you will start now, yeah. Let me pack everything and get out of here. If you don't, you know, make things get,